So this is one of the first videos we're going to be uploading onto our new Lab of Legends website, and it focuses primarily on the big question: what is science and why are we learning this? Now, for many of you, you probably walk into a science lab, you sit down, you open the textbook, you answer questions, then you leave. All right? And no one could blame you. Not everyone enjoys science. However, many people ask, "Sir, why are we learning this?" Here's the answer, the ultimate answer. Because you need to learn how to question things. Now, for many of you, you think, "Oh, I can question stuff. Oh, what's that? Oh, what's that? Oh, what's that?" That's not really asking a question. In science, we're all about exploring the natural world. We want to understand why things are the way they are and how can we use them better to our advantage. Now, we do this through what's known as the scientific method. Okay, it's very similar to an engineering designing process if you're more of a hands-on kind of person. The scientific method always starts with a question. You want to understand how something works. For instance, my lab assistant Squidly here wants to know why gravity works. So, why does gravity work? Why is it that whenever I let go of Squidly, he falls directly to the table? Who knows? From there, we need to find out who would know. We do research. We ask ourselves, who else in the entire span of human history has asked the exact same question I'm asking now? From there, we might think, okay, they've sort of answered my question, but not well enough. I need to do the test myself. I want to understand exactly why this is happening. So, Squidly might want to make a prediction about gravity. And the prediction is often in the form of a causal relationship. If A happens, then B happens as a result. If I let go of an object, then it falls to the ground. And we're going to go into that a little bit more later. Now, after you made a prediction, you make a test to see if it works. If it does work, or if it doesn't work, either way, you still have to analyze your results. You want to examine why this still happened. Because in your results, if you do enough tests, you can pick up on trends and you can predict what's going to happen later on quite accurately. The last part is probably one of the most important pieces. Science is not an individual endeavor. No scientist works 100% alone. They always have to work together. So if Squidly discovered something new about gravity, for instance, only blue things are affected by it, then naturally he would put forward his findings to other scientists and they would want to find out exactly what's happening. If for whatever reason his test wasn't that good, another scientist will pick up on it. It's much like how you ask a friend to check over your work, or you ask your mum or dad to check your spelling if you've done homework, because you want to know if you've done a good job, and often you can't see your own mistakes that well because you're a bit too close to it. Now, this as a whole, you might not use outside of a lab your entire life. You might go off and you want to become a hairdresser, you want to become a fitter and turner, or you want to become a test pilot. But one thing that you will use that's very similar is an engineering design process. Nearly every single one of us at some point in our lives is going to build or fix something. And to do that, we use this same process. So to start with, you might ask yourself what you need to build or what you need to fix. It might be, I need to build something to get me across a river, or I might need to fix this particular PowerPoint, or whatever. Don't do the second one unless you're a trained electrician. You then might do research on how to do this. How do I make a piñata? How do I, fix the leaky tap in the sink? You then think to yourself, okay, I've got a pretty good idea now. So you might imagine yourself, how are you going to tackle this? If you're not confident, you hire a handyman. If you are confident, you do it yourself. If you're sort of confident, then you need to learn. Okay, it's never going to hurt learning something new. Unless, of course, it's something you can't unsee. The next part will be you have to make a plan. Okay, I want to be able to fix this table. Now to do that, I need to make a plan. I need to know what I need to get for it, such as materials, tools. I need to know where to find those things. I need to know how much it's going to cost me. Very much a practical-minded plan before you start. Measure twice, perform once. The next step is to create it. So the next step is to put into practice what you've been planning. So I want to fix this bench. I need to actually go to Bunnings. I need to buy the materials. I need to come back. I need to roll up my sleeves even further, turn this into a singlet, and start fixing this table. Afterwards, I need to ensure that I've actually done this thing correctly. So the best way I can test is see if I fix this bench correctly. Put stuff on it. Put your body weight on it. If you want to test if the leaky tap's actually been fixed, you turn it off and on a couple of times. Make sure there's still water coming through and it does not leak when it's turned off. The last step is optional. It depends what kind of thing you're doing. If you're building something, fantastic, you built it. But then you might think to yourself, hang on, what if I did this to make it a little bit better? So then you go back in a whole circle all over again because you want to improve on what you did. My dad is very big on, hunting. And every time that he's taken a rifle out into the bush and he's gone shooting for wild pigs or foxes or rabbits or whatever, he comes back and he thinks, okay, this worked well. However, could I improve this a little bit more? And then he starts tinkering with it and he takes it out again. He continuously does this process over and over again because he wants to ensure that every time he uses this rifle, it's the best possible opportunity for it to be the best version of itself. So while you might not use this, I can bet you folding money you will use an engineering process. But enough about that. You probably want to hear a little bit more about how to do a little bit better in class. So if that's the case, let's have a look at this version. This is a layout of how exactly you're going to perform a science experiment in class to make your teacher happy and to stop annoying you. And we start with the title. Okay, your title is essentially, that thing. Oh, that thing. Okay, it tells us what the focus is for the entire deal. So it might be brands of potting mix versus plant growth. Okay, from that title alone, you can tell that I want to see whether or not a different brand of potting mix is going to make a plant grow taller. From there, we have our aim. It's a statement or question or objective that you want to address. So, after that, we have your hypothesis. Very similar to your prediction. I think that this is going to happen because of this. It uses the typical layout of if, then, because. So, if, then, because. Okay? This talks about a causality. So, for instance, if I use potting mix brand A, then the plants are going to grow taller because potting brand A has the type of nutrients needed to make this plant grow. Okay, I've identified the thing that I am changing on purpose, the result of that change, and why it happens. Now after that, we have what's known as our variables. Variables are factors that affect an outcome. So in science, we try to control all of them bar one or two. So if you've ever been to an athletics carnival or a swimming carnival or any sort of competition, you know that the game has rules. The reason why it has rules is to ensure that it is a fair game, which is to say that the only way to determine whoever wins the game is based on who's performing certain skills better than the other team or the other competitors. For instance, the 100-meter sprint. high school classic, okay? You have 8 people lined up at one end of a 100-meter track. You have a marshal next to you. When he says go, you run as fast as you can. Whoever gets to the other end first wins. Now, the variables that you control is which person is running. So if you want your team to win, you'd pick the fastest person, obviously. The dependent variable is what position they come when they run the race. Do they come first, second, third, wooden spoon? So that's the thing that you are observing or measuring, okay? The last part, the controlled variables, are the variables we have to keep the same throughout. For instance, no one is allowed to stand on the track when the race is running because it interferes with it. If there's an interference with the race, then obviously we can't tell who's the fastest because it could have been some other thing that caused it. Same reason why everyone has to start running once the starting gun has gone off. If people start running beforehand or they only start running a few minutes afterwards, that's not an accurate gauge of who's the fastest runner. The next part is safety. So if you're looking at an experiment and you have a whole bunch of chemicals and pieces of equipment around you, and you want to ensure that it's safe enough to use, you have to do a safety evaluation. This is quite simple. All you do is you identify first all of the possible risks associated with the experiment, like if I use a beaker, it could break in my hands. So glass cutting me is a threat. Or if I'm using water, I can slip on it. Hence, that is a possible threat. And then from there, we find out ways to prevent these risks from being major issues. For instance, if you're looking at using acid, then you wear protective equipment. If you're looking at using electrical appliances, you ensure that the power is turned off if you're fixing things. Okay? You identify the risks, then you find ways to mitigate the risks. From here, we swing around to materials. We know for a fact that you can't perform an experiment without stuff. So you need to make an inventory or a list of everything you plan to use for the entire experiment. This includes quantities. It's much like how with cooking, you need to have a recipe list or a list of ingredients, I should say. So you include what ingredients you use to make the thing, and you include how much is required. For instance, you need 200 grams of flour. You need 250 milliliters of milk. You need 2 eggs. Okay? With an experiment, it's the exact same deal. The only difference is you're also going to be including any appliances or any equipment that you're using. So if you were to, say, make this more like a cooking show, then you would also be including, I need spoons, I need a large flat pan, I need an oven, I need this, that, and the other. Okay? From here, we go into the method. Now, the method is quite simple. It's a list of instructions that someone else has to perform. The problem is with most people is that when they write out a method, they do so thinking that's very simple to them. However, it has to be simple enough or it has to be clear enough that anyone else who picks up the experiment can perform it as well. So this is why we tend to use the terms clear and concise whenever you're writing a method. Okay? So if I were to, say, use Squidly as an apprentice and he wants to learn how to perform a certain experiment, I need to ensure that my instructions are clear enough that Squidly can follow them and get the exact same results or similar results. Okay, if I use super complex language or if I use hundreds of thousands of overly simplified instructions, Squidly's not going to perform it exactly. And it's going to impact on the quality of the experiment. Your results. Your results come in the form of you measuring or observing the experiment as a whole. What's happening in your test? You know, did you see a color change? Did you see new matter being formed? Did you time something? Did you measure something? All of this information needs to be recorded, even the stuff where you screw up. Because if you remove any bit of information, that builds into a horrible habit called cherry picking. If you start cherry picking information, it means you're only taking in the information that you want to see or hear. It's much like how if you only listen to things you want to hear from other people, rather than actually listening to the entire thing they're trying to tell you, I mean, it's not particularly useful. For instance, if your teacher is giving you feedback on a report, then you need to listen to everything that they have to say, good and bad. If you only listen to the good, or if you only listen to the bad, you're not getting the whole picture. Everyone knows that selective deafness is very irritating to deal with. Then once you've gotten your results, you start going to the discussion. This is very similar to our research stage and our analyzing stage here in our scientific method, whereby anyone who performs an experiment has to look at their results and then ask themselves why they think it happens. This is very much of the because or the reason why certain things occur. Now, the discussion is going to be at least several paragraphs long, each paragraph containing a different idea about why things happened. One paragraph that's always important to include is your analysis of the experiment itself. Do you think that was the best possible test? Did your test break down, or did you make a mistake somewhere, or could you improve on it? You need to be able to review your own work effectively in order to become better as a science student. Your last part is your conclusion. The conclusion itself is like any conclusion, really, in a book. It wraps everything up in a nice, neat bow, and it goes back to addressing your aim. So the aim might have been to test whether the color of a car impacts its speed. Your conclusion would be something like, in conclusion, there is no evidence to support that the color of a car impacts on a car's speed. This is because the color of a car is the preference of the buyer. It has nothing to do with the operation of the vehicle. Okay? So you talk about how it links back to the aim and you justify why it happens. Okay, so at this point, that is everything you need to know about performing science, particularly experiments. Okay? So if you have any questions, please ensure to like, subscribe, or at least send us a quick message through our Instagram page if you want to know more or you want to make a particular request on a certain topic. It could be anything from different types of rocks to the Newtonian laws of physics. It could be talking about how cells work. Anything is up for grabs, but please ensure that you are specific with your questions, and we can keep them anonymous if you'd like. As always, I've been Forry, you have been amazing. I'll see you legends around.